Good morning, everyone. Our project is called Frequency Aware Multitask Learning for Generalizable Deepfake Detection. This is our first milestone presentation presented by Nadia and Amal. What is our project about? Nowadays, deepfake detectors perform very well in controlled lab setting, achieving over 97% accuracy in clean benchmark data. But when the same model is tested on compressed videos or videos that it didn't see before, which is possible to encounter in real world, performance drops significantly. In our case, the model we used, IECCE, drops from 97% accuracy on clean C23 videos all the way down to 74% on heavily compressed C40 videos and any videos it didn't see before. This 23% drops is what we call the generalization gap, and the core goal of our project mainly is to try to close this gap as much as we can. Moving to the data set we are using, we mainly use two data sets, face forensics and wild deep fake. Face forensics plus is our training data set. It contains 1,000 real videos and 4,000 fake videos generated by 4 different manipulation methods. We use the official split of 720 for training, 140 for validation, 140 for testing. We test on both C23, which is tightly compressed, and C40, which is heavily compressed, to simulate real world conditions. And the second milestone, inshallah, will be using wild deepfake in our cross data set evaluation set. It contains over 7,000 real world internet videos and will be used to test how well our model generalized beyond the lab.
Moving on to the survey of existing methods. Moving on to the survey of existing methods. So as you can see, the RECCE model performs best across all benchmarks, and while there is still a generalization gap present, as you can see on the Face Forensics Plus, it has a 93% EUC score, while on the wild deepfake it only performs 64.3%. While there is a generalization gap, it's better than the rest of the models. For instance, having SBI performing a 63 on the wild deepfake, while a 93 on the Face Forensics Plus, and so on and so forth can be observed for the rest of the models. Now, why we chose RECCE or RECCE as our baseline? So as previously mentioned, it performs the best cross data set generalization that we currently have. In addition to that, we have all the pre-trained weights and the code publicly available. Then one of the most important things that it's a reconstruction-based approach. So the reconstruction-based approach learns what a real face looks like rather than memorizing fake artifacts, which is the foundation for generalization. And fourth and most importantly, it has clear documented weaknesses that we can target with our improvements. Then moving on to the RECCE architecture. RECCE works by reconstructing the input face using an encoder-decoder architecture. Real faces reconstruct well, but fakes fail because the decoder was only trained on real faces. The reconstruction error is then used by the guided attention module to highlight the manipulated regions. The reasoning graph module fuses the features across multiple scales to capture both local and global artifacts. Finally, a binary classifier is used to identify whether the output is real or fake. So our proposed solutions or our proposed improvement to RECCEs are three. So the first one involves using a frequency branch that applies FFT transform to detect GAN fingerprints that are invisible in the spatial domain but clearly visible in the frequency domain. Secondly, CBAM attention, which adds channels in spatial attention at 3 encoder stages to focus on manipulation-prone regions. Lastly, a multitask head that adds extra supervision during training to manipulation type and mask prediction heads. Only the binary head is used at interface. During this milestone, we focused on the implementation and the testing of the frequency branch. In future milestones, we'll be focusing on the implementation and testing of the CBAM and the multitask head, and potentially fusing them all together.
Moving to the proposed frequency domain improvement compared to the baseline, which only use special features with no data augmentation, our first milestone changes added three things. The first thing is the frequency branch itself, which is used fast Fourier transform to detect the GAN fingerprint and frequency domain, and a learned gate blend these features into the special features gradually during training. Uh, After we did this, we found like a slightly overfitting. That's why we added in the second run compression data augmentation to simulate C40 like condition during training. Then in the third run, to try to enhance the performance more, we tuned the number of frames from 4 to 8 and increased regularization with higher dropout to reduce overfitting. Moving to the results, as we can see in the table, our here our results across three training runs. But firstly, the baseline, we can see that it performed 97% on C23 and 74% on C40, and the gap between them, as we said before, is 0.23. Then in the first frequency, when we applied the frequency domain and the 4 frames, we find that C23 we found that C23 reached 97.37% and C40 reached to 68.30. 68.34 with a gap between them 0.2903. And the run 2, when we added the data augmentation, which brought the gap slightly below baseline. And in run 3, we combined and as we can see in the second run, we found that the C23 accuracy is 92.60 and C40 is 69.65, and this made the gap to be 0.2295, which is slightly below the gap between the baseline, but we still didn't reach the accuracy we want to achieve to be above the baseline. For the third run, we combined augmentation and increased the number of frames. Big video, this recovered the C23 accuracy to 96.2 while maintaining C40 at 73.3, giving us the small generalization gap of 0.22. 9. The key finding here is that the frequency branch alone is not enough. Augmentation and more frames are both needed to see improvement. Moving to our confusion matrix.
Moving on to our confusion matrix. So first off, let's look at the confusion matrix for the C23. So looking at this, all 4 runs perform well on the C23 data. The baseline correctly classifies most real videos and the fake frames. Run 1 shows a slight improvement in real detection, while run 2 has more misclassifications due to the model adjusting to the augmented training data, and run 3 recovers well with very few errors on both real and fake. And then moving on to the C40 confusion matrix, the challenge is clear across all models. The baseline already struggling, missing around 3,800 fake videos, which is expected since the model does not know how to generalize well, as seen in the statistics in the survey. And run 1 performs the worst, missing around 4,300 fakes. Run 2 and 3 gradually improve, and this indicates to us that we are moving slowly but surely in the right direction. So in run 3, it shows the best balance, correctly identifying most real videos at 9,380, while still catching 7,030 fakes. The model still misses about 4,160 fakes. So as Amal mentioned, we still have room for improvement by combining the CBAM approach or the multitask head approach in order to further with the frequency in order to improve our results. And as for our timeline, we aim to implement the CBAM and the multi task head first, and then we aim to train all three variants together, and we aim to test different, for instance, different variations of combinations, so CBAM and frequency, frequency and multi-head, or all three together. And then we aim to compare all three improvements versus the baseline, and then we will take the best combination or the best model output and give it the wild deep fake. And after that, we will have the final training with the best configuration after the testing. So we're going to test on the wild deepfake, and then we're going to train on the best configuration, and generate all required figures and write the final report. Thank you.